Alright, so the last time we were looking at quaternions and then understanding that how the representation of rotation between two coordinate frames, which we saw previously in terms of Euler angles, could now be related in terms of quaternions. So we introduced the concept of axis angle rotation or the simple rotation, where we define an axis about which the rotation happens by a certain amount of angle. That angle is denoted as beta, and that axis about which the rotation is happening is denoted as a unit vector called lambda. And we saw that in that case, the rotation matrix can be given in this format, where we have the identity matrix plus sine of beta times s of lambda plus 1 minus cos of beta times s of lambda squared, where S of lambda is a skew-symmetric matrix based on the unit vector lambda. And the main idea here was that we can now start introducing the idea of a quaternion as a 4-parameter system which consists of one real part and 3 imaginary parts. And the first idea which we introduced is that of an unit quaternion, which means that if I take the norm of the quaternion, it turns out to be 1. And a set of all such unit quaternions is termed as capital Q. Then we saw that the axis angle representation which we had can be modified slightly in order to fit our quaternion approach. But before that, we defined what the quaternion parameters are and how do they relate to the axis and angle. So the real part of the quaternion is actually nothing but cosine of the angle beta by 2, where beta is the angle by which we are making the rotation about the axis lambda. And then we also saw that this imaginary component of the quaternion, which is the epsilon, was given by lambda times sine of beta by 2. So notice that epsilon is not a unit vector, although lambda was a unit vector. Alright, so armed with that, we see that this representation naturally satisfies the quaternion's requirement that the norm is equal to 1. Then we define the idea of product of two quaternions. So when I take a Hamiltonian product or a product of two quaternions, I end up with another quaternion, and this is how we go through the algebra in order to get what the components of that product are. We notice that because of this last term, S of epsilon q1 times epsilon q2, this term causes a problem in the sense that because of this term, the product of two quaternions is not commutative. So if I take a product q1 cross q2, that is not equal to q2 cross q1. Notice, however, that addition is commutative. So q1 plus q2 still is q2 plus q1. Then we try to understand how we can express this rotation matrix in terms of quaternion parameters, and we saw that we could express that neatly using this axis angle variation. And the rotation matrix is now purely parametrized in terms of the quaternion's parameters. So this is in difference to what we saw with the Euler angle. So when we looked at the rotation matrix about 3 orthogonal directions, we saw that that gives us a Euler angle representation where the terms depend on phi, theta, and psi. Whereas when we are looking with the quaternion representation, the rotation matrix is expressed in terms of eta, epsilon 1, epsilon 2, and epsilon 3. And that being the main difference. But please understand that for a particular Euler angle, if we calculate the quaternion for that Euler angle set, then the rotation matrix from both should be the same as long as we are not in the singularity condition, which means that if our rotation matrix is singular for the Euler angle representation, then they won't be the same. But as long as we are not near the singularity, the rotation matrix should exactly be the same. We also looked at the angular velocity transformation, where we try to understand that how we can express the rate of change of a quaternion with time, and we saw that that could be expressed in terms of a cross product between the quaternion and the quaternion formed out of the angular velocity of the body. And I told you that this expression actually comes out from our rotation matrix differential equation, which we had talked about in the previous lectures. We go ahead and substitute the quaternions into this rotation matrix and then try to figure out what the derivatives of the quaternion terms look like and then collect them together to form this equation. We also talked about the idea that during an assignment, we'll try to see that this is giving us the same matrix representation as before. Okay, then we talked about the 6th degree of kinematic equations using quaternions. The only difference here being that we now have 4 additional parameters instead of 3 additional parameters. So in the Euler angles, we had 3 angles. Here we have 4 parameters. And then we describe the dynamics or the kinematics in a similar manner. One important point which we discussed about yesterday was that quaternions must be unit quaternions, which means that we have to ensure that as we keep integrating to find out what is the new value of the quaternion at a new time step, we must be aware about the idea that the norm should still be 1. So whenever we are doing the computation of the new quaternion from the old one by doing the numerical integration, we must normalize it so that its value becomes 1. We also looked at finally about the conversion between unit quaternions to Euler angles and how the Euler angles can be converted into can be expressed in terms of the quaternion parameters. And I think that is where we left off yesterday. Okay, any questions so far? Yes, no?
No, sir.
No, sir.
No questions so far. All right. More of this may probably be more clear once we start discussing about the quaternions in the assignments. So there we should see more, something more come up. Okay, so today we'll proceed further. All right. So far we looked at the idea of transformations between the body frame. We looked at how to convert the vectors which are expressed in the body frame to NED frame. And then we also looked at how we can do the opposite. So that is what we have been discussing so far, and that's where our kinematics has been focused on. But we also need to look at the transformation between the Earth-centered Earth fixed coordinate system, ECEF, and the NED. This is sometimes required because when we have some sensors, they're not necessarily measuring quantities in the NED frame. So for example, when you have your GPS sensor does not measure the positions of the craft in the NED frame, but rather it measures them in the Earth-centered Earth fixed frame. So it is important to understand what is the transformation which is happening between the ECEF to NED and also from NED to ECEF, how this transformation is performed. So in essence, when I am given a latitude and a longitude, how can I go about finding where exactly is my craft located on the ground? How do I say where is it located? So that is what we are going to discuss about today. Everybody with me so far?
Yes, sir.
Yes, sir.
All right. Okay, fantastic. So just like as before, we know that the kinematics of the position vector, so time derivative of the position vector in the Earth fixed frame, notice that ECEF is denoted as the Earth fixed frame E. So we are looking at the position of the body's origin with respect to the Earth center expressed in the E frame. That position vector's derivative is nothing but some rotation matrix RNE, where the rotation matrix is converting things from the N frame to the E frame times the velocity of the body with respect to the N frame. Is this making sense? Is this part making sense?
Yes, sir.
Okay, just like previously we had previously NB dot in N frame was given by a rotation matrix from B to N times the velocity of the body in the B frame. This is how we had a similar kind of a expression we are right now writing between the E frame to the N frame. So it's kind of similar, but only here the rotation matrix is from the N frame to the E frame. Now, this vector, which is the position vector of the body with respect to the Earth center expressed in N frame, that velocity can further be written as RBN times VEBB. Is this making sense? Yes, no?
So the velocity in the body frame and then convert it into the N frame.
Correct. So the velocity here is in the N frame. I'm converting that into the velocity in the B frame. So therefore, I introduce this second rotation matrix from B to N.
Yes, sir.
Okay. Now the velocity is in B frame multiplied by this rotation matrix. This part will give me the velocity in N frame. And this entire part will give me the velocity in E frame. Everybody with me so far?
Yes, sir.
Yes, sir.
Okay, all right. Now, this rotation matrix, which you saw here, okay, that is the rotation matrix from the N frame to the E frame. I'll define that as a function of some angles between the E to the N frame. And those angles are nothing but the longitude and the latitude. Okay. All right. Now, and this part we already know. The rotation matrix from the N frame, from the B frame to the N frame, we already know this expression. It can be expressed in terms of Euler angles or in terms of quaternions. When in that case, the rotation matrix would be denoted as this. In either form, we can denote it. But today's discussion will be more to talk about how we are going to talk about these things, the rotation matrix or the transformations from the N frame to the E frame and vice versa. That is what we are going to discuss today. Okay. Notice that this rotation matrix RNE is formed by considering two principal rotations. So we are taking a rotation about the z-axis. So if I have the Earth, okay, and let's say that this is the polar axis, and I call that ZE. Okay, and then if I'm actually considering at any point at the NED frame, then what is happening? I'm drawing a tangent at that plane, and then I'm pointing the Z direction to be normally inside. That is Zn. Is that making sense?
Yes, sir.
That is how we defined an ED frame, right? North, east, and down. So it is Down means it is normal to this tangent plane of the Earth. And then X is pointed in the north direction, and then Y is accordingly decided based on the right hand rule. So in order to move from the XEYEZE frame to the NED frame, we need to first transform by an angle which is equal to the longitude, which is defined as the angle from the x-axis to the tangent location where we are trying to compute the things. Okay. So in this case, it will be all the way till here. So that will be the longitude. And then the latitude will be the direction this fellow makes with the horizontal. That will be mu. Now, don't worry about this picture. I know this picture was not done properly to scale, but we will redraw this picture. The picture is there below and we'll discuss about it. So it is composed of two rotations, rotation by L about the z-axis and a rotation by minus mu minus pi by 2 about the y-axis. So let me see if I can actually get this picture out. Should have the picture somewhere. Yeah, page number 34. All right, so this picture will do much more justice. Let me do that. All right. This is the picture from your textbook actually. So notice that suppose I am drawing a NED plane here where you see my mouse pointer. So the X is pointed towards the north, the Z is pointed normally downward, and the Y is pointed based on the right hand convention. And the E frame is located at the center of the Earth or the center of mass of the Earth with x-axis and y-axis in the equatorial line and the z-axis along the axis of rotation. Okay, the angle L is denoted as the plane where I am taking the NED frame. So where the XZ plane of the NED frame lies, that plane, how far away it is from the x-axis. That angle along the equatorial direction is called the longitude. Is that making sense?
So this x-axis is along the prime meridian.
Correct. So the x-axis is pointed around the prime meridian. So it will be in line with the Greenwich Observatory. So this will correspond to 0 longitude.
Yes.
Okay. And then from there we are measuring the longitude direction based on the positive convention with respect to the ZE axis, with respect to this axis. Everybody with me?
Yes, sir.
Yes, sir.
Okay. Now you will see that one funny thing which you see is that the normal to this plane doesn't necessarily pass through the center of the Earth.
Yes, sir.
Okay. And the reason for that is because the Earth is not exactly a sphere. If it were a sphere, when I draw a tangent plane to it anywhere, the normal should pass through the center. But since this is not a sphere, it's more like an ellipse. So therefore what happens when I take the tangent plane, it need not necessarily go through the center. But that's fine. What that normal direction makes an angle with the equator plane, that angle is defined as mu. That is our latitude. Yes, no,
Yes, sir.
making sense?
Yes, sir.
All right. So that is our latitude, and this is our longitude. Now,
So is this the latitude will come from the equator, right? And so it doesn't pass through the Earth's actual that our ECF frame's origin.
correct, it does not. It doesn't have to pass through the ECF frame's horizon.
Okay.
It passes through the frame only when this fellow is located either at the pole or at the equator. Then that normal will pass through the center, but at other times it need not pass through it because it is an ellipsoid. Okay, that is the main idea. So this is a confusion as to when you consider latitude, you would have imagined that I draw a line from the center of the earth to
Yes.
the origin, and what that angle it makes would be latitude, but no. Because that line would not necessarily be normal to the tangent plane which I'm drawing.
Yes.
Right? So we are more interested in this thing being oriented in the down direction, normally downwards to the tangent plane, and x being oriented along the north and y being oriented along the east. So that is why we will define this plane first based on wherever it is tangent to the ellipsoid of the earth, and then based on that we formulate the normal, and that need not always pass through the center of the earth. Okay. Any more queries? Anything else which is troubling? Okay, excellent. So then we can come back to our correct. Okay, so the rotation L is about the z-axis, which is about the longitude, and then the rotation is about minus mu times minus pi by 2, which is about the y-axis. And you will wonder why this minus pi by 2 has come into the picture. That is to make the range of the angle proper. Okay. Okay, so in essence, I can specify the rotation matrix from N to E as a rotation about Z by an angle L, followed by a rotation about Y by an angle minus mu minus pi by 2. So if I look at the rotation matrix, I'll get cosine of L, sine of L, this rotation matrix about the Z axis, and then the next is the rotation about the Y axis. Is this making sense?
Yes, sir.
It's making sense? For
Yes,
me,
sir.
it's not. So let me go back actually, just to convince myself that we are doing this right. Okay, so we have a rotation about the z-axis by an angle L. Okay, and then we are rotating by the eventual y-axis by an angle minus mu minus pi by 2. That is actually not making sense to me. Let me come back.
So like this Z is the ZE one, right?
Correct. ZE. About the ZE, first we are making a rotation in order to get this x-axis to coincide along this line, right?
Yes.
After the L rotation, the x-axis will be pointed here, right? And it will be pointed normally out.
Like that will also rotate that YE towards like
Well, Y will be perpendicular to that, right? It will be into the paper or something like that.
so after we rotate with about YE, like that will turn that angle.
But why is it minus mu minus pi by 2? That's what I am thinking.
Oh,
That angle, see, my contention would be that if ZE now should point in the Zn direction, if ZE must point in the Zn direction, it
oh,
should,
so like it should go below, right?
yeah, that's what I was thinking too. That it should be actually positive is this. Okay, minus mu. Minus mu minus pi is what I would have thought. Yeah, you see, minus mu will bring it to the z-axis will point in the opposite direction to Zn.
After first rotation about ZE, XE is pointing along this line, right?
Correct, about this line.
And YE has gone like rotated, and it is
Correct.
perpendicular to that.
Correct.
After
So,
the ZE is still pointing upwards.
correct. So therefore, now we are rotating by the y-axis.
About that YE, the rotated YE, about that if we rotating like in minus mu minus pi by 2 along as shown, like this is positive mu, but if we go in opposite direction to that, like minus mu minus pi by 2, about that YE.
So if I go above the YE by minus mu, then what will happen? My x-axis is now pointing in this direction. Yes, and then another 90 degrees it will point in this direction. That is what it means. So it is correct. Okay.
So this ZE now turns completely down, like
yeah, ZE will be down then. After I do the rotation by mu and minus pi by 2. Just imagine, okay, so once I rotate by the angle L, XE is here along this line. Okay?
Yes, sir.
Now, the next rotation about Y is going to happen in this gray plane. Right? So when I rotate by the angle mu, minus mu, it will, x-axis will now point in this direction, opposite to Zn.
Why is that minus mu?
First let's rotate with minus pi by 2. So
no, first rotate by minus mu. That is when you will see why the pi by 2 is coming. First rotate by minus mu. Notice that the y-axis is pointing inward, right? So the positive orientation would try to bring it down. The x-axis will come down. If I make a positive rotation about the y-axis, the x-axis will go down, isn't it?
Yes.
You're not following me? Tell me if you're not following me. If I take a rotation about the y-axis, positive rotation about the y-e axis, the xe axis will go down.
Yes.
Right? So that is why the minus sign. That is why I have to do minus mu. So once I do minus mu, it will go up. Right? So now that xe axis will be pointed up parallel to this Zn axis, only the direction is opposite.
Yes.
Right? So the direction is exactly opposite of Zn direction. Another pi by 2, if I rotate, it will now orient in the north direction.
Yes.
Is that clear for everybody?
Yes, sir.
Shadab?
Yes, sir.
Okay, so that is why the minus mu minus pi by 2. Okay, so it will, this minus mu will orient the x-axis opposite to the Zn axis, and 90 degrees will rotate it in the north direction. Will orient itself in the north direction. All right. Good that we looked at this. So that is why we will have first a rotation by an angle L about the z-axis, followed by an angle minus mu minus pi by 2 about the y-axis. So that is why our rotation matrix from R and E will look as a composition of the matrix due to this multiplied by the matrix due to this. We can express that combine and simplify it, and that RNE, so the rotation matrix to go from N frame to E frame, can be given as a function of the latitude and longitude, and is given by this expression which we see here. Okay. All right, so let us formally define the latitude and the longitude, since we are going to be talking about this more. We know that the Earth is actually not a spherical quantity, it's not a sphere, and it actually can be approximated as an ellipsoid. And the World Geodetic System 1984 was established in order to determine what is the ellipsoid which the Earth really represents. And this is more of the accepted nomenclature today. So we denote that as WGS 84 as the ellipsoid or the reference ellipsoid. About which we are assuming all of the calculations in a GPS coordinate system. So let us understand what this ellipsoid means and how is it looking like. So the origin of this ellipsoid coincides with the center of mass of the Earth. So it is at the center of the Earth. Now, it is an ellipsoid which is obtained by an axisymmetric system, which means that if I take this ellipse, which you see in the vertical plane, where the axis of rotation is the vertical axis, so the Earth is actually rotating about its axis like this, then you see that actually the Earth's shape doesn't look like a circle, but rather it looks like an ellipse, where the semi-major axis and the semi-minor axis are different. So the larger radius is called the semi-major axis, which is the radius of the Earth along the equator. And the other axis, the semi-minor axis, is the radius along the poles. All right. And you see that we are actually constructing a ellipsoid or an ellipsoid by actually taking an axis of revolution as the vertical axis, and we revolve this ellipse about that axis to get our actual ellipsoid, which is a 3D geometry that the Earth represents. Is that making sense?
Yes, sir.
Okay, so along the equator, the radius of the Earth is the same all along the equator. We don't assume that it changes along the equator. So it is axisymmetric. So we take this ellipse and we simply spin it around along the vertical axis, and you'll get the ellipsoid that you're looking for. Okay, everybody with me so far?
WGS 84 that defined the RE and RP.
Correct. So RE and RP basically define this ellipsoid. Okay. So that is our radius along these poles. And in fact, you'll see that the radius is quite significantly different. So 6,378 kilometers, not 6. Otherwise, I have to call it 6,378,137 meters is the equatorial radius, whereas the polar radius is given by this. If you see roughly, it is about how much is the difference? 78 minus 56, roughly.
22.
About 22 kilometers, right?
22.
Yeah, roughly about 22 kilometers is the difference, which you'll see, plus or minus a little bit more because I'm not accounting for the decimals here. So that is the difference in the radius in the polar direction compared to the equatorial direction. Now, and Earth is rotating about its axis once every 24 hours. So that correspondingly gives us our angular velocity of the Earth frame with respect to the inertial frame, and that is given as 7.292115. This is nothing but 2 pi by t, where t is actually 24 hours. I express that into seconds and then I convert it into radians per second. This is the value you should get. Now, the eccentricity of the ellipsoid is defined as 1 minus RP by RE squared, square root of that. Okay, and that eccentricity of the ellipsoid for the Earth is about 0.08. So it is more or less closer to a sphere, but still it is not exactly a sphere. Is that making sense, what I mean by this? Yes, no?
Yes, sir.
All right. Okay, now let's come back to our talking about our NED frame. So what we do is we are drawing a tangent. So suppose this is the point of interest to us. Okay, and here we are kind of generically putting the point way above the Earth's surface. So especially if it says that I have a satellite, right, that I want to track in a terrestrial navigation system, then that point's coordinates is x, y, and z. Okay.
Yes, sir.
Now I drop a perpendicular from that point to the tangent plane of interest to me. Okay, so I want to drop a tangent such that this angle is 90 degrees. The line from joining from the perpendicular line to the tangent plane, which is passing through that edge. That is the line that I'm interested in. And when I extend it further, you'll see that it actually doesn't necessarily intersect at the center of the Earth.
Yes, sir.
Okay, now I want to find out where this line intersects the vertical axis. That distance from that point till this tangent plane I denote as n, capital N. Okay. And the distance above the Earth's surface from the tangent plane till the point of interest, that is what I represent as h. That is the height at which it is. Okay, so this is the height of the object above the tangent plane to the WGS 84 ellipsoid. Okay, that is what I want to find out, and it is the perpendicular distance from that plane where we are standing. Everybody clear on the convention so far? It's not that complicated, it's pretty simple, isn't it?
Yes, sir.
Yes, sir.
Yeah. All right, so now we define the latitude, the height, and the n. So n, which we define, that is called the radius of curvature in the prime vertical. Prime vertical because we are looking primarily in the vertical plane, and it is axisymmetric. So therefore, no matter where I cut, the point is looking in the vertical plane. So in the prime vertical, I am interested in what is the radius of curvature at that local point, and that is given by n. Okay.
Yes, sir.
Okay, that is my local radius of curvature, and it keeps changing as I come to the pole, right? That radius of curvature will become RP. As I come to the equator, that radius of curvature will become RE. And in between it will vary. Okay? Yes. All right. Now, these things are drawn a little bit exaggerated. In general, you'll see that this n will be pretty close between RP and RE. Now, the figure here doesn't show that because my drawing is not so great, but please take me on my word that this n will not be significantly different from RP and RE. It will be somewhere between them.
Yes, sir.
All right. Okay. Now, the latitude, which we call as the geodetic latitude, as we already discussed, is defined as the angle this line makes with the equatorial plane. That angle is called the latitude angle mu. So when we are at the equator, what will be the value of this latitude?
G.
0. And when we are at the pole,
90 degrees.
it will be 90 degrees. Good. All right. Now, this n, which is the radius of curvature, can be shown to be equal to re square divided by square root of re square times cosine square of mu plus rp square times sine square of mu. Typically comes from ellipsoids properties, but you can really, if you want, you can go and verify. Now, the longitude L is given by, if I want to find out, so suppose that I am given the coordinates of xe, ye and ze, and I want to find out what is the corresponding longitude, what is the latitude, and the height of the thing above the tangent plane. So I want to transform xe, ye, ze into L, mu and h. That is what is our first target. We'll try to see, given that I know where xe, ye and ze is, how do I compute the latitude, longitude and height? The longitude is straightforward. I simply take what is ye divided by xe, tan inverse of that. That should do the trick for L. Is this making sense?
Yes, sir.
We come back to our picture here. I am simply interested in wherever the point is, what is its x and y directions relative to that. In the equatorial plane only I am interested. So at this point it will be the distance here divided by the distance here, right? That is what I will take. This distance versus this distance. Is that making sense? Suppose the point is here. I'm interested in this point here in the equatorial plane. Okay, then I'm really looking at what is the ye value and what is the xe value, and those two will determine where my longitude direction will be. Does not depend on the z. Yes, no.
Yes, sir.
Yes, yes, sir.
Okay. So by point, wherever it is located, I'm only interested in this and this to determine what my longitude is. But when it comes to the latitude, all three will play a role. So the longitude is the simpler of the two. It simply is the tan inverse of y by x. The latitude and the height, they are kind of implicitly related. So which means that the latitude depends on the height and the height depends on the latitude. Okay, because we are taking a tangent plane, and where the tangent plane lies will depend on what the height is, and as the height changes, the tangent plane will also change. So they are both implicitly related, and the equations for those are given here. So tan of mu is given as ze divided by p times 1 minus e square n by n plus h, whole thing inverse. Notice here E is the eccentricity which we defined. And P here is nothing but square root of xe square plus ye square. That's what you have here. All right. Now I'm not showing the proofs for these. We are going to just believe in the geometry of an ellipsoid and go forward from here. Okay, we're not really interested in a mathematics class where we want to show a proof for them, but it can be shown. you can find standard textbooks on GPS, which can explain why these relations are coming in from the standard ellipsoid geometry that we assume. Now, because these two are implicitly related, we will need to solve for these iteratively until we get a convergence. So because if we find a mu value and a h value, we need to iteratively change. As mu changes, h will change. As h changes, mu will change. And we have to make sure we go through the process until the convergence is achieved. So in essence, if I want to look at a algorithm for that, let me talk about that. Yeah, here. So given three coordinate systems in the ECEF frame, XE, YE, and ZE coordinates in the ECEF frame, and if I want to convert them into latitude, longitude, and the height, my step one would be to calculate this value of P, then compute an approximate value of the latitude, where I am substituting as ZE by P times 1 minus E square, inverse of that. Notice here that I'm assuming that this value is roughly about 1 when I take an approximate answer. I'm taking that to be approximately 1 during approximation, during calculation of mu 0, the first estimate of the latitude. Is that making sense?
Yes, sir.
Once I get an estimate of the latitude, I can then compute the value of n and then go ahead and compute the value of h. Okay, so I got mu 0, h0, let's say. Once I get h0, I can use that to compute a better value of the latitude, which will be my mu1, where I can precisely put these values in. Okay.
Yes, sir.
Now, once I get mu1, I can check whether mu1 minus mu0 is small or big. If this value is big, is greater than some known epsilon tolerance that I set, okay? This is some tolerance value that I set. If it is greater than that, I say that, okay, go ahead and now compute h1. And then go back and compute mu2 using h1. And then look at the difference between mu2 minus mu1. If that is less than or greater than epsilon. So suppose that one is less than epsilon. Then I say, okay, I terminate my value here. Mu2 is the value of the coordinate and equivalently h2 is the value of the height. Is that making sense? How that iterative part is working?
So initial values need not be like you assumed n upon n plus h to be 1. It need not be 1, right? Means we can start anywhere.
You can start anywhere, but we take that value to be 1 because then by taking that value to be 1, mu is independent of h. Mu doesn't depend on any more h, right?
Yes, yes.
So that is a good starting point.
Yeah.
Because mu doesn't depend on h, I can compute this precisely and then I can keep iterating. The next part I bring in n by n plus h. And that h gets updated, it will update the mu will again update the h will again update the mu, and this process continues until mu converges.
Yes, sir.
Okay, so as long as if the mu minus mu0 is less than some tolerance value, then the iteration is complete. Otherwise, you set mu0 equal to mu and then continue the steps 3 to 6. And this keeps on going until the convergence happens. So that is the process which will tell me once I get, so this is basically telling you that if I am given a value of xe, ye, ze, I can how to compute L, mu and h. L can be computed from these two quantities directly, but mu and h we have to solve iteratively. Okay? Yes? No?
Yes,
Yes,
sir.
sir.
Yes.
No. Now, this is what we have shown here, as Aditya just rightly pointed out. There was no reason to choose n by n plus h as 1 and then apply this formula. You could have started at a different starting point also. And true. And not only just that, there could be a slightly different algorithm also. So what we have shown is one of the many algorithms, and this algorithm that we have shown is the one which was followed by this seminal paper or seminal book on Hoffman and Wellenhoff et al. 1994. This book has pretty good information about GPS systems. So I think the title of the book itself is Global Positioning Systems. Okay, so if you want, you can take a look at that to get more detailed understanding of how these geodetic systems work and how the geodetic systems impact a calculation of our exact position of height and the latitude. It's usually the height which is of most concern, especially when you're doing something like a survey. You've sometimes seen people doing surveys, right? Before building a building, they will be doing some surveys and trying to scope out what is the height or what is the height of the earth at different locations. And then based on that, they will try to come back and say, this is how my surface looks like with respect to some datum line, which either can be the WSG tangent plane or it can be something called as a geodetic data. Now, we are not really discussing about all these quantities, so we will not be talking more about what these are, but these are used mostly for surveying applications. And that is where much of the what you call development in the GPS for survey applications brought out many of these formulations out. Okay, so now we understand that if we are given three coordinate systems, three coordinates of a point in the E frame, how can I express them as a latitude, longitude, and a height value? That much we have understood today. Tomorrow we will try to look at the opposite thing, and we'll try to also understand what this height exactly means. Is this the real height that we are interested in or not? Because many a times we are not interested in this height with respect to WSG84, WGS 84, but rather we are interested in the height from the mean sea level, let's say. Correct? That's how we mostly measure the height, isn't it? Height from mean sea level. How can this height which we computed as h can be related to that height is what we will talk about tomorrow. Okay, on Monday. Because we are out of time. All right. All right. So that will be all for today. Any questions before I stop?
Sir, this height h for any object on the surface, on the flat plane, that will be 0, right?
If it is on that tangent plane, it will be 0. Correct.
And our ships and vessels, they mostly operate on that.
No, you will see that it is not so, because this is saying that suppose the earth is an ellipsoid. Okay, so let me kind of put it here. Yeah. So let us say that the earth is an ellipsoid. We are approximating it as an ellipsoid. An ellipsoid is a very smooth surface. Please understand that. Correct? It's an ellipse which is always very smooth, and I'm rotating it about one axis, so the resulting thing will also be smooth. But in reality, that would not be the case. So my ellipsoid surface might look like this, but my actual geodetic line might look like that, because I may have a I may have a Mount Everest coming in here, or then I might have an ocean and a deep trench coming in here, and that's how my actual Earth might look like.
Okay.
Okay. In fact, this also is not quite right. The ellipsoidic line might look something like that. You never know. Okay.
Yeah.
What I'm really interested in is when I have my sea. From that sea level, what is the height? That is generally what is of interest to us in a surveying applications, right? H from mean sea level. But what you got as the height now is the height from the ellipsoid. This is the H that you calculated now.
Yes.
Right? So these two have to be related in some sense. Right?
Okay.
We have to make a transformation from one to the other. And that is what we'll discuss when we talk about it on Monday.
Yes, sir.
Okay, we'll not be going into too much detail. These are some of the concepts we just want you to appreciate and have a sense for them that, oh, okay, there is a height which I'm measuring from the mean sea level. There is a height which I'm measuring from the smooth ellipsoid surface. They both are not necessarily the same. So how do I transform one height into the other? We'll not exactly be understanding exactly how the transformation works because it's not so material for us. For most of our cases, we'll only be needing the latitude and the longitude. We are not really interested in the height in our dynamic positioning problems. Right? The height is of less significance to us. But it is good to understand it and keep a perspective with us as we move forward. All right?
Yes, sir.
Okay, so then we'll stop today at here. We'll stop recording.